Have you ever stopped to wonder what's really going on inside your phone or your laptop? I mean, it's not just a random jumble of parts, right? It's this whole world of incredibly clever engineering hiding right there in plain sight. Well, today, we're going to pull back the curtain on one of its coolest, most elegant secrets.
Okay, think about this for a second. We do this every day. You plug your phone into a standard 5-volt USB port, but your phone's battery, it only wants about 3.7 volts. So if you just wired them up directly, you'd completely toast the battery. So how does your phone handle that extra voltage? How does it do it safely and super efficiently, every single time?
Well, the secret is a tiny little circuit called a DC to DC converter. And honestly, it's one of the unsung heroes of all modern electronics. Its whole job is to take one voltage and perfectly transform it into another. It's the reason our gadgets work at all. And the way it pulls this off, well, it's surprisingly clever.
So before we can crack open the circuit itself, we need a basic toolkit. Now, don't worry, this isn't going to be some heavy physics lecture. As we'll see from the source material for this, a brilliant MIT lecture on the topic, we really only need 4 simple, super intuitive rules to understand the whole shebang.
And here they are. First, voltages in any loop have to balance out to 0. Think of it like walking up a hill and then back down. You always end up right where you started. Second, current can't just vanish. Whatever flows into a point has to flow out. And these last two, these are the secret weapons for these circuits. Over one full on and off cycle, the average voltage on an inductor is 0, and the average current through a capacitor is 0. That's it. That is our entire toolkit. Let's use it.
All right, let's put that toolkit to work with our very first circuit. This one is called the buck converter, and its job is to solve our phone charger problem, taking a high voltage and efficiently bucking it down to a lower one.
So how in the world does it do it? Well, the core idea is actually pretty simple. The circuit uses a super fast switch to literally chop up the incoming high voltage into a stream of tiny pulses. A good way to think about it is like flipping a light switch on and off thousands of times a second. Your eyes wouldn't see it flicker, right? You just see a dimmer, average brightness. While the circuit does the exact same thing with voltage, and then a filter comes in and smooths out all those pulses into a perfectly steady, lower voltage.
Now, the key to controlling that final voltage is something called the duty cycle. It sounds fancy, but it's just the percentage of time that the switch is in the on position. That's it. This one number is the control knob that lets engineers precisely dial in whatever output voltage they need.
And this makes the relationship crystal clear. Look at this. If your input is 10 volts and your duty cycle is 0.2, meaning that switch is on just 20% of the time, your output is exactly 2 volts. You crank that up to an 80% duty cycle and your output becomes 8 volts. It's just this beautifully direct and totally predictable relationship.
And it all comes down to this simple, elegant equation. The output voltage is just the duty cycle multiplied by the input voltage. That right there, that's what's happening inside your phone charger right now, turning 5 volts into the perfect 3.7 volts your battery needs, just by tweaking how long a tiny little switch stays on. So cool.
Okay, so stepping voltage down kind of makes sense, right? You're just taking a piece of what's already there. But what if you need to go the other way? What if you've got a little 1.5 volt battery, but you need 5 volts to run something? For that, engineers use something called the boost converter, and this is where things get really, really interesting.
But wait a minute, how is that even possible? It feels like we're breaking some fundamental law of physics here. How can you get more voltage out than you put in? Are we just creating energy out of thin air? The answer is, of course, no. But the way it works is so clever it almost feels like magic.
Okay, so it works in 2 steps. In step 1, the circuit switch connects the input voltage directly across a component called an inductor. This makes the current ramp up, and as it does, it's basically charging that inductor by storing energy in its magnetic field. Think of it like you're pushing a kid on a swing. Each push stores a little more energy into the swing's motion.
Then, in step 2, the switch flips. This suddenly changes the path of the circuit. The inductor's magnetic field collapses and it releases all that energy it just stored. But here's the trick. That released energy is now in series with the original input voltage. They literally add together, creating a total voltage at the output that is higher than the input was by itself. The swing has reached its peak.
And this right here, this is the secret behind the magic. As Professor Perol explains in his lecture, an inductor has this really unique property. It hates changes in current. So when that switch flips, the inductor will do whatever it takes to keep its current from stopping suddenly, even if that means generating a massive voltage spike.
The boost converter brilliantly harnesses that powerful physical kick to create a higher voltage whenever we need it.
And of course, there's a simple bit of math that proves it. The output voltage is the input voltage divided by 1 minus the duty cycle. Now, since D is always a fraction, it's always less than 1, that number on the bottom is always less than 1, which means the output voltage is always going to be greater than the input. The closer you get D to 1, the higher the voltage boost.
So we have the buck to step down and the boost to step up. And these aren't just some abstract circuits from a textbook. They are the absolute workhorses of modern technology, silently managing power in pretty much every single device you own.
So where do we find them? Honestly, the better question is, where don't we find them? They are all over your smartphone, managing dozens of different voltages for the processor, the screen, the radios. They're in your laptop, your TV, the powertrain of your electric car, even in the systems that take power from a solar panel and feed it into the grid. They are truly, absolutely everywhere. When you really look at it, the solution is just pure elegance. It's not about some exotic new material or super complicated components. The secret to all of modern power electronics is the simple idea of switching things on and off very, very fast. And it's not just clever, it's incredibly efficient, often over 90%. Almost no energy is wasted as heat, which is exactly why these little circuits are at the very heart of our portable, battery-powered world. At the end of the day, what these circuits do is they transform a fixed, kind of dumb power source like a battery into an incredibly flexible and smart one, able to deliver whatever voltage is needed, efficiently and precisely. It's a foundational concept that really did enable the whole portable electronics revolution. And it just makes you wonder, with such a powerful tool in their hands, what new technologies will engineers power up next?